In this section we're going to be working with the mean value theorem, but before we do that we're going to look at a kind of a special case of the mean value theorem called Rolle's theorem. Now Rolle's theorem is easily explained with pictures, and then we'll go ahead and write out a formal definition as well. So Rolle's theorem basically gets at the idea, if we have a curve, and it can be any shaped curve, but it has to have a special case occurring, and that's at point A and point B, any point A and any point B, and it could be more than one time that this happens. The value for f of A and the value for f of B is the same. So this y value basically is the same at A and at B. So this would be f of A, which equals f of B. So that's basically saying the y values are the same. Well, what Rolle's theorem basically says is that somewhere between A and B there is at least one, so there could be more than one, so at least one point at which this function f has a horizontal tangent line. So Rolle's theorem, it almost looks a little bit more secant, so Rolle's theorem guarantees at least one time, if these cases hold, that I have this horizontal tangent line. Now let's remember what a horizontal tangent line is. That means the derivative is equal to 0. So the point that's guaranteed by Rolle's theorem and eventually by the mean value theorem is C. So there's some point C in the interval AB where I have a horizontal tangent line. Well, if I have a horizontal tangent line, that means the derivative evaluated at that point is 0. Now let's go ahead and write this out properly, and we'll look at a couple of things about an open and a closed interval here as well that have to be true in order for Rolle's theorem to hold. So let's go ahead and write it out formally. Let f, that means your function, be continuous, and it has to be a continuous function, and it has to be continuous on the closed interval AB. And it has to be differentiable. Now remember, in order for a function to be differentiable, it has to be continuous and can't have any of those sharp corner points. So put that on the next line. And it has to be differentiable on the open interval AB. Now the reason we don't include the closed interval here is I can't say I'm differentiable at an endpoint here because I'd have an infinite number of tangent lines. And f of A equals f of B. That means the y values for x equal A and x equal B are the same. So these are the criteria that must hold in order for Rolle's theorem to be true. Now the result then that I can conclude from Rolle's theorem, if this is true, is that there is at least one point. There could be more than one, but there's guaranteed at least one point, and this point is called C, that's in the open interval AB, such that the derivative evaluated at C is equal to 0. That's guaranteeing the horizontal tangent line. So for Rolle's theorem, this is the criteria that must be met before I can apply it, and over here in the purple is the result of that then. Let's go ahead and look at a different shaped graph with Rolle's theorem as well. Let's say we had a graph with a couple of turns in it. And with these couple of terms we can look at the A, some value of A. Here's A. And then let's come over here to some value of B. Now what Rolle's theorem guarantees is if I have this f of A equal f of B, which I certainly have here because basically the y values are the same for A and B, that guarantees that there'll be at least one horizontal tangent line in the interval. And we can see we have one here and another one here. So that's another picture of how Rolle's theorem could work, where I'm showing at least one point. In this case I'm showing 2 points. So that's Rolle's theorem. It's a special case of the mean value theorem. And when we get to the mean value theorem, we'll kind of see what one of the differences is. Now before we go on to the mean value theorem, I'd like to work a problem involving Rolle's theorem. So an example using Rolle's theorem. One of the things we always have to be sure about is we must verify that I can even apply Rolle's theorem. If I had a function that was not differentiable on an endpoint, or was not differentiable at every point, then I'd have to be really careful. For polynomial functions, I don't need to worry because, of course, polynomial functions are always continuous and differentiable. But other types of functions I might need to be concerned with. So to get started, let's go ahead and find an interval. So this one, we're not given AB, we have to find AB. So find an interval on which Rolle's theorem applies. And let's go ahead and pick a nice polynomial function for our first one to get started. Let's go ahead and use f of x equals x times x minus 1 quantity squared. Now this is a polynomial function. We might not recognize it as such because we're used to having it written out in terms of our highest degree of the polynomials and they decrease. But this is a polynomial function. The reason we have it written like this is it's already in factored form, so it makes the problem a little bit easier. Now there could be a lot of different intervals here. We are just asked to find one. Then once we find those points that make up the interval, then we're going to find all the points C in the interval, and there could be one or more points, we're not sure how many yet, in the interval AB. And again, we haven't established what that interval is yet, at which f prime at C equals 0. So before we actually solve this, let's go ahead and draw a bit of a picture. This is x times the quantity x times x minus 1 quantity squared. So I think it might be useful to graph this real quick. So let's go ahead and graph this on our calculators. There's lots of nice online graphing calculators as well. Desmos is one of them. If this was a problem on a test, I would give you the graph, so you wouldn't be expected to graph that. So to start graphing, we hit y equal and roll clear, and our function was x times the quantity x minus 1 squared. And we might have to adjust our graph a little bit. Now there's quite a bit going on here, and it kind of looks like it's flat through here. I'm going to change my window view. I want to see more of what's going on my y min and y max. I want to zoom in on that a little bit, so I'm going to change those. And I bet we'll see a bit of a curve, and you can't hardly see it at all, but there is a curve starting to show there. So I'm going to go on my y min, y max, -1 to 1. And again, this is just an iterative process that you can go through and change the settings until you can start to see clearly what's going on. So this is the same exact function that we've been working with, but what I have here is I have a good view of what's happening with this curve. My earlier screenshots of this would have been not very useful because I would not have seen that change. So let's go ahead and pop this in, and let's see some points that we think are reasonable for the mean value theorem. So looking at this graph, I need 2 points that have the same y value basically. So there's no other point that has a y value up here, none down here. So I'm going to have to choose some right in this interval. Looks like between 0 and 1. So in fact, I think 2 easy points to use would be 0 and 1. So I want to choose, just from looking at this, the points of 0 and 1. Now I could have gotten this from this factored form as well. X is 0, x minus 1 equals 0, x equal 1. I can see that that will occur. So the points that I want to choose are going to create the interval 0 to 1. And again, there's other ones that I could have picked, but these look like some very obvious ones. So my interval that I have from A to B, my closed interval 0 to 1, is definitely differentiable. It's continuous and differentiable on that interval as well. Now the reason I chose this is that f of 0 and f of 1 are both equal to 0. So if I plug 0 in, or if I plug 1 in, I get 0 back out. So that tells me f of A equals f of B if we want to think about it in terms of our original Rolle's theorem. Now what I want to do is I want to find the value of C guaranteed by Rolle's theorem. And it kind of looks like to me it's going to be right here is where I have that horizontal tangent line. F prime of C equals 0. So I'm trying to find this value of C right here. So this is the value of C guaranteed by Rolle's theorem, and I want to figure out where that is. So we need to find where the derivative is equal to 0. So to find C, in the interval a, b, where I guess we know our points now, so we'll put that in as 0, 1. We need to figure out where f prime of c equals 0. Well, this is a review then. This is basically finding a critical number by taking a derivative and figuring out where that critical number equals 0. So I need to take a derivative and set it equal to 0, find critical numbers, check them in a slope chart, or use that first derivative test. So that's kind of the process that we're going to go through here. Okay, so let's go ahead and look at that. My original function, I'm still working the same problem, x times x minus 1 quantity squared. And I want to find the derivative. I could use the product rule here, or if I wanted to, another thing that I could do is I could expand this and rewrite it as a nice polynomial expression. And it doesn't matter which way you choose to do this. You'll get the same answer in the end. You'll get x cubed minus 2x squared plus x. So these are all equivalent expressions. So to find f prime of x, I'm going to use just my polynomial. I could have used the product rule up here, but I like my polynomial here. So I'll have 3x squared minus 4x plus 1 equals 0. So I'm trying to find the 2 points where this is equal to 0, and the reason I set it equal to 0 is so I can find the critical numbers. Now remember, critical numbers occur 2 places. The critical numbers occur when the derivative is equal to 0 or where the derivative is undefined, but you can see we don't have a denominator and we don't have any radicals, so I don't need to worry about that. Now it's my grand hope that this thing factors. So let me go ahead and try a few here. So let's try 3x and x, 1 and 1. I think we can make this work if these are both negative. Let's double check it. Minus 3x. Yep, this works great. So I have 3x minus 1 equals 0 and x minus 1 equals 0. Solving, I get x equal, I'd add 1 divided by 3, x equal 1/3. That kind of seems reasonable. It looks like it could be a third of the way through, and I have another one at x equal 1. Now, this is an important point here that we need to make about the difference between the value of 1/3 and the value of 1 when we're talking about Rolle's theorem. Now remember, my interval was the closed interval 0 to 1, but the value of c I'm looking for is in the open interval 0 to 1. So when I come down here and I'm looking at this value of 1, I can kind of eliminate it because it's not in my interval from a to b or 0 to 1. Because this is an open interval, meaning I never quite reach 1. So x equal 1/3 is the value that is guaranteed by Rolle's theorem. I should say I hope it is. We still need to check it. Now if truly this does have a horizontal tangent line, I would put this in a slope chart, and in my slope chart I should see a change in concavity. So my slope chart, I don't need to check 1 because it's not in my interval here from 0 to 1, my open interval 0 to 1. So here's x equal 1/3. And again, I'm really only checking values from 0 to 1, points not included. So I need to check a derivative value somewhere to the right and a derivative value somewhere to the left. But I can't choose a value like 2, 3, 4 because I'm only checking between 0 to 1. I could check a value, let's say like 1/2. And down here to the left of 1/3, I can't check something like a 0 or -1. It has to be between 0 and 1/3, points not inclusive. So I could check something like a 1/4. Okay, so where am I going to check these? In the first derivative. So I come up here to my first derivative. I'm going to look at this in factored form. If I plug a 1/2 in here, I get a negative. If I plug a 1/2 in here, I get 3/2 minus 1 is a positive. A positive times a negative is a negative. And so I know that this is decreasing. I don't know about its concavity, I just know that it's decreasing slope. The slope is negative. Now over here to the left, let's go ahead and plug in a fourth. So 1/4 minus 1 is going to be a negative number. 3/4 minus 1 is going to be a negative number. A negative times a negative is a positive. And so you can see that I have increasing to decreasing. So what I have here is a relative max. And because I have a relative max, that tells me at f prime of 1/3, this is equal to 0, producing a maximum, a relative maximum point. So my slope chart helps to establish that. You can also use the first derivative test, but I really do like the idea of the slope charts. Now you could do this with a trig function as long as it's continuous on the interval and differentiable at all points on the interval as well. And somewhere in this lecture, I don't know if we'll do it with Rolle's or with the mean value theorem, we'll do this with a trig function just so you can kind of get an idea of how it works with functions other than just polynomial expressions. Okay, let's go ahead. Yeah, let's do a trig function now. Now most trig functions are continuous on an interval, not always. So this is going to be another example of Rolle's theorem. We'll work with a nice sine or cosine function because those are continuous over all intervals. Tangent, you'd have to define the interval to be where we're continuous because we have those vertical asymptotes. So for our example, let's go ahead and be given an interval this time. We're not going to come up with our own. And let's go ahead and look at, find the value of c guaranteed by Rolle's theorem. And before we find the value of c, we have to make sure, first of all, that all the criteria are met for Rolle's theorem of the function f of x equal, let's do a trig function, let's do the cosine of 4x. And please always put parentheses around the arguments of your trig functions. It helps keep things pretty clear when we're taking derivatives and combining terms. And let's be given an interval this time instead of finding our own. And that interval will be the closed interval, pi over 8 to 3 pi over 8. Okay, so first of all, we need to establish that this is actually applicable to Rolle's theorem. So what is the criteria for Rolle's theorem? Okay, it has to be continuous and differentiable on the interval. And it is continuous and it is differentiable because it's the cosine function, and the cosine function is continuous from negative to positive infinity. So I think we're good here. So the criteria has been met. Now if this was another trig function like a tangent, I'd have to double check to make sure there were no vertical asymptotes in the interval. So to get started, I want to find the value that's guaranteed by Rolle's theorem. And this value of c has to lie somewhere between pi over 8 and 3 pi over 8. So I need a derivative. Now, I think it might be interesting to look at the graph of the cosine of 4x before we get started. So let's go ahead and pop it into our curve here. So we have cosine 4x. Now, when we graph this, a couple things I'm not sure about is my calculator in degrees or radians, and I can see right up at the top I'm in radian mode, so that's good. So we can see this is definitely continuous. Now my interval only goes from pi over 8 to 3 pi over 8. That's a very small chunk of the first quadrant basically, so it's right in here. So I'd like to take my x-axis and I would like to focus more in what I'm looking at. So this is negative 5 radians, so that's almost negative 2 pi but not quite. And this goes up to positive 2 pi. So I think I would like to go from negative pi to positive pi. And this might even be too much. We'll have a look. Let's graph that and see what it looks like. That's a little better. What we're looking at is pi over 8 to 3 pi over 8. So we're looking at something in this first quadrant because this is pi over 2. So we're trying to focus in on just this type of area right here. So let's go pi over 8 to 3 pi over 8. Let's go 0 on my left endpoint for my window, and for 3 pi over 8 that's almost pi over 2. So let's go 0 to pi over 2. Let's go 0, and then pi over 2. And again, I'm just trying to get a good look at what's going on with my graph. Okay, that's a lot more useful. So let's take this screen snip. Let's get an idea of what's going on here. And again, if this question was on a test, I would have the graph for you, and then you could find the values and the points that are occurring. Okay, so pi over 8 to 3 pi over 8. If I want to look at pi over 8, let's go ahead and plug that into my function. Let's plug in f of pi over 8. This would be cosine of 4 times pi over 8. So this would be the cosine of 4 pi over 8 would be pi over 2, and we know the cosine of pi over 2 is 0. Okay, so this is, I'm looking for the point. When I plug in pi over 8, I get 0 back out. So I'm thinking that pi over 8 is probably right about here. Let's go ahead and do the same thing with 3 pi over 8. These are not derivatives, I'm just plugging into my original function. 4 times 3 pi over 8. Simplifying this, I'd get 4 goes into 8 twice, so I'd be left with 3 pi over 2 here, and the cosine of 3 pi over 2 is 0. So this is my other endpoint of 3 pi over 8. So basically what I'm saying is somewhere between these 2 points, I'm trying to find the value of c guaranteed by Rolle's theorem where I have a horizontal tangent line. So I'm looking for right here on this picture, f prime of c equals 0. Well, if I trace this back up, this is my point C. Now what I don't know is what is the point C that makes this true. This is the value that's guaranteed by Rolle's theorem, but now I need to figure out where it is. Well, to find this value of C, I need to take a derivative, set it equal to 0, find our critical points, test them in a slope chart. So find C in the interval pi over 8 to 3 pi over 8. These are fun problems. So I want to know where f prime of c equals 0. So I need a derivative. So remember f of x on this was, I've forgotten already, cosine of 4x. So f prime of x is going to be equal to the negative sine of 4x times 4. The derivative of the cosine of u is negative sine of u prime. I'm going to rewrite this so we have that coefficient out front. This would be negative 4 sine of 4x. And I would like to figure out where this is equal to 0. Well, to get started, we could divide both sides through by a negative 4. And I have the sine of 4x equals 0. So this is a little bit easier to solve. So in order to figure out where the sine of 4x equals 0, I'm going to take 4x, I'm going to say, well, I know that the sine is equal to 0 at 0. At 0 radians, the sine is equal to 0. I also know that the sine of 4x is going to be equal to 0 if the argument of 4x equals pi over 2. So those are a couple of pieces of information that I know. Now I know that this is going to happen every pi units. So what we have occurring here then, solving this trig equation, this is true here, and it's true again here, and it's true again here when I hit again. So if you want to think about that as 4x equal 2 pi, 4x equal, whoops, this should just be pi, not pi over 2. What am I thinking? I have it right in the picture, but I wrote it incorrectly. This would be 3 pi. But you see that there's a pattern here. So it goes 0, 1 pi, 2 pi, 3 pi, 4 pi. So I can start trying to solve this. And so if we divide through by 4 here, I get x equals 0. Divide through by 4 here, and I get x equal 2 pi over 4 or pi over 2. If I solve for x here, I get x equal pi over 4. If I solve for x here, I get x equal 3 pi over 4. So I have all these possible solutions, and I even have negative solutions that I haven't looked at, but I'm not really interested in the negative solutions because my interval, remember, was pi over 8 to 3 pi over 8, which is positive. So these are some potential solutions for us to look at. I have 0, I have pi over 4, I have pi over 2. These are just going up by pi over 4 intervals. This is neat. And this continues on and on and on. Now, where does pi over 8 fall in this? Well, pi over 4 is 2 pi over 8. So this is equivalent. Our interval goes from pi over 8 to 3 pi over 8. So somewhere between pi over 8 and 3 pi over 8 is this value of 2 pi over 8. And that's the value of C guaranteed by Rolle's theorem. So I had to do a little fun trig equation solving there. I like that. But I do need to check this in a slope chart first. So let's go ahead and check this in that slope chart. Now remember, for our slope chart, it's basically a number line. This number line is going to go from the open interval pi over 8 to 3 pi over 8. And I'm checking the value of pi over 4, or if you wanted to think about it as 2 pi over 8, you could as well. So 2 pi over 8 and pi over 4 are equivalent. And the reason I'm writing it as 2 pi over 8 is they have the same denominator then, and sometimes that's a little bit easier to think about and compare. So what are some numbers I could check? I need to check numbers to the left and check numbers to the right. Well, there's not a lot of gap going on between 2 pi over 8 and 3 pi over 8. If I want to think about these as 16ths, I could. So this would be 4 pi over 16. This endpoint would be 6 pi over 16. So a number in between here, or an angle that I could check, would be 5 pi over 16. There's a lot of other ones that you can check, but this is just kind of an easy way to find that, is to have that common denominator and then look for a gap. Pi over 8 would be the same as 2 pi over 16. So if I want to check between 2 pi over 16 and 4 pi over 16, the easy thing to do is 3 pi over 16. Now, when I'm looking at this, plugging, where is my derivative? Oh, here it is, clear up here, negative 4 sine 4x. I can plug in 5 pi over 16. If I plug in 5 pi over 16, I'd have 4 times 5 pi over 16. I just care whether it's positive or negative. This would be 5 pi over 4. Huh, that's interesting. That's going to be a negative, but we'll check it out here and I'll explain why that is. This is a negative 4, so this piece is a negative. This piece is also negative, and a negative times a negative is a positive. So this will be a positive here. So it's increasing. Now, if it's going to be increasing, whoops, I forgot to explain why the sine of 5 pi over 4 was negative. Sine of 5 pi over 4, well, if you check out the unit circle, here's 4 pi over 4, here's 5 pi over 4, and we can see that the sign is negative in that third quadrant. Now over here, I'm guessing we're going to decrease, but we better double check. So I'm going to plug in 3 pi over 16 into my derivative. Remember, my derivative was negative 4 sine of 4x, so this would be 4 times 3 pi over 16. Okay, the same thing happens here. The 4 cancels into the 16 4 times, and I'm left with 3 pi over 4. So this is a negative. Sine of 3 pi over 4, if we jump back over here, is in my second quadrant where the sign is positive. Negative times a positive equals a negative number. So this is a relative min. This is the value of C guaranteed by Rolle's theorem. So 2 pi over 8, which reduces to pi over 4, is the value guaranteed by Rolle's theorem. So C equals pi over 4. So another way we could write that is f prime at pi over 4 is equal to 0. So the interval pi over 8 to 3 pi over 8 contains that value pi over 4 where the derivative is equal to 0. And in fact, it's a relative min, which is kind of some added information. So we've spent quite a bit of time on Rolle's theorem, and we still haven't gotten to mean value theorem, which is the section of this, or the section name of this lecture. So we better get on to the mean value theorem. Rolle's theorem was a special case of the mean value theorem. The mean value theorem doesn't limit itself to the slope of the tangent line having to be equal to 0. So that's the difference between Rolle's theorem and the mean value theorem. All the criteria are the same for both. They have to be continuous and differentiable on an interval. But the difference is the mean value theorem I can go a little bit further with, in that I can find the slope of any line, not just the slope of the tangent line equaling 0. Now, of course, Rolle's theorem is nice because I'm finding relative extrema, but we already know how to find it relative extrema. Now, a couple of things to remember. The derivative determines whether a function is increasing or decreasing. So the derivative is also rate of change. So those are the two things we kind of want to keep in mind with the mean value theorem. So the derivative determines whether a function is, you know what, we haven't ever talked about constants, so let's put in all three of these. Whether a function is increasing, decreasing, or constant. So constant is one we really haven't talked too much about, but we will. So that means, remember, that f prime of x is also an idea of the rate of change. Now remember, the rate of change was the change in the y values over the change in the x values, like slope. So if your function is increasing, that tells me that the derivative is positive. If your function is decreasing, that tells me then that the derivative was negative. Now, if my derivative is equal to 0, so notice I have less than 0, greater than 0, but what about equal to 0? Then I have constant. F of x is constant if my derivative equals 0. So I could look at a function, let's say, that's increasing, decreasing, and then it could switch out to be constant. So this is increasing. This side is decreasing. And of course here we have our derivative is equal to 0 is constant. Now this is not, my derivative is equal to 0 here as well, but this is an entire line that's constant, not just a single point. So that's kind of something to remember. So let's go ahead and write out what the mean value theorem says technically, and then we'll have a bit of a picture to go along with it to help clarify it. So as usual, we are going to assume our function is continuous and differentiable on the closed interval AB. And I should say, I kind of messed this up, is continuous on the closed interval AB and differentiable on the open interval AB. Remember, it's those endpoints that make the difference there, so I need to make sure I have that right. So this is the criteria that must be met for the mean value theorem. If this criteria is met, then I can say there exists at least one value C so there could be more than one, that is in that open interval such that basically the slope of the tangent line equals the slope of the secant line. Now the way we're going to write this out is f prime at c equals f of b minus f of a all over b minus a. And so to clarify this, this is the slope of the tangent line. And this expression on this side is the slope of the secant line. Now you might say, well, wait a minute, how do I tell the difference? Well, remember, secant has 2 points. Tangent is a single point where I have a tangent line. Secant line goes through 2 points. So another thing that we could talk about is the idea of there exists at least one tangent line that is parallel to a secant line in the interval. So there exists at least one tangent line that is parallel to the secant line. In the open interval AB. Well, let's go ahead and look at a picture of this. Pictures always help clarify what's going on. So we always seem like we use this upside down parabola, so let's kind of keep with that same shape. Let's go ahead and look at our values for A and B. So we have a value at A, value at B. These are equal, and I don't want them to be equal because then you might think of Rolle's theorem, and they don't have to be equal. So I want to move these around a little bit. So I'm going to move A over here. I'm going to move B over here. So you can definitely see that f of A and f of B are not equal here. So you can clearly see that this is a secant line, and if I want to figure out the slope of the secant line, I would take the change in y over the change in x. So this point right here is f of A. This point down here is f of B. So the slope of the secant line would be the change in y, f of A minus f of B over A minus B. If you want to change the direction, that would be f of B minus f of A all over B minus A. So what this is saying then, if I keep moving this secant line, let's say to this next point and the next point, and I stay parallel to it, at some point this secant line is going to turn into the tangent line. And that's the whole idea behind the mean value theorem right there. And what that's saying is the slope of this secant line and the slope of this tangent line are going to meet at this value of C. Now notice this value over here, of course, was f of A. This value over here, if we look across, was f of B. And here this value is f of C. So I'm looking for this value of C where the slope of the secant line is equal to the slope of the tangent line in the interval. So this is just kind of a nice pictorial of what's happening there. Now we're going to actually have to go through and figure out where this occurs. So for our next one, let's look at not a polynomial function because we've looked at a polynomial function. Let's go ahead and look at a radical expression. So this example demonstrates the mean value theorem. So as usual, we want to find the value C. That's guaranteed by the mean value theorem for the function f of x equals root x on the interval, let's do 4 to 9. Okay, so we can draw a quick little picture. This is a graph that we don't need to use a calculator for because we should know the graph of the square root of x. And we kind of want to make this a little bit steep. The square root of x is actually quite a low slow growing function. So I'm going to make this probably a little bit steeper than it actually is. So I'm going to say that this is 4 and this is 9. So get rid of this on the end. So 4 and 9 is my interval. Well, I know when I plug in 4, square root of 4 is 2. I'm going to get 2 back out. When I plug in a 9, square root of 9 is 3, so I'll get a 3 back out. So this is the secant line that I have right here. Oops, I'm going to miss it. Let me see if I can sketch that in a little bit better and try and hit both points. Okay, let's try that again. So I want to hit both points, and it has to be a straight line. I'm going to keep moving this line up and up and up, staying parallel to it until I find the line that is tangent to it and tangent to the curve and parallel to the secant line. So this is the value of C that I'm looking for. So this is the secant line and this is the tangent line. So I want to figure out where the slope of the tangent equals the slope of the secant. Well, we can kind of logic our way through this without a formula, but the easy way to do this is to say, well, f prime, because that's the slope of a tangent line, is the derivative, and this is happening at value c, which we don't know, we're trying to figure out, is equal to the slope of the secant line. Now there's several different ways we can find the slope of the secant line. One way we could do f of b minus f of a all over b minus a. That's just the change in y over the change in x. And I could do f of a minus f of b if I wanted, as long as I did a minus b in the bottom. So let's go ahead and have a look. F prime at c. Well, let's call 4a and 9b. So f of b was right up here at 3. So this is f at 9. This is f at 4. So f of 4 was equal to 2 all over b minus a. Well, that's 9 minus 4. So I get 3 minus 2 is 1, 9 minus 4 is 5, and I get 1/5. So I get f prime of c is equal to 1/5. Well, this is helping us a little bit along the way. The formula is definitely getting easier, but really I need to figure out what is f of x. Well, f of x, I guess I don't have to figure it out, it's given to me. I need to figure out f prime of x. That's 1 over 2 square roots of x. Now if you need to work that out, that's fine, that's x to the 1/2. So if I took my derivative, I'd bring the 1/2 down, decrease the exponent by 1, and then I rewrite this negative exponent down into the denominator. So basically I have 1 over 2 root c, and the reason I'm going to call it c is I need f prime at c. So this is f prime at x. F prime at c is 1 over 2 root c equals 1/5. So I need to solve this. Several different ways we could solve it. I think I'll start by cross multiplying. So I get 2 root c equal 5. Divide both sides through by 2. Root c equals 5/2. Square both sides, and I get c equals 25/4. So this is the value guaranteed by the mean value theorem of 25/4. Now this is only going to be true if this falls within the interval 4 to 9. So let's go ahead and see if it does. This as a mixed number, 4 goes into 25 6 times with a remainder of 1, so that's 6 1/4. So there's the value of c guaranteed by the mean value theorem. That definitely lies between 4 and 9. And for whatever reason, when we hit calculus, we don't use mixed numbers anymore. So let's go ahead and put our answer in as the improper fraction 25/4. But switching it to a mixed number showed me that yes, it does lie between 4 and 9. So this is the value of c guaranteed by the mean value theorem. So that's pretty cool that we could come up with that. Change the endpoints, it's going to change the value of c because the slopes change. Now another interesting thing that we can infer from what we've been working on will help us solve a lot of different types of the application problems that we'll see. This one, I'm just going to look at a quick graph. And let's go ahead and say that this is point A and this is point B. So here's point A and here's point B. Whoops, I better scoot it over. My graph ran off the page. Say this is point B. Well, looking across then, this is f of A. This is the y value that I get when I plug A in, and this is f of B. Well, another thing the mean value theorem is going to imply then is that as I travel from A to B, my function is continuous and differentiable. That guarantees then that every value between f of A and f of B is touched somewhere. It's reached somewhere. Another way we could look at this is if I'm driving and I'm going from speed 45 to speed 55 from time 1 to time 2, I had to hit every speed in between 45 and 55. So this is guaranteeing that I'm achieving every value between f of A and f of B by the mean value theorem as well. Okay, so again, a nice little thought of that would be, let's say at time 1, I am traveling at 45 miles per hour, and at time 2, I'm traveling at 55 miles per hour. Now in between these, maybe I accelerated, decelerated, but every single possible speed between 45 and 55 had to have been achieved between time 1 and time 2 in order for me to get from 45 to 55. There were no jumps. There was no miracle skip from 45 to 50 all of a sudden. I had to hit every single possible value between those. And so when you look at the application problems, I'd really encourage you to graph them. That's going to be very helpful to you. You might not know the shape of this curve in between, but you can start by graphing the points and then inferring what you need to about snowpack or speed or drag racing, temperatures or something like that that you'll see in your different types of homework problems. So again, picture's worth 1,000 words. It's going to help you out a lot. You might not know the exact shape of the graph in between, but you will be able to get the endpoints and then know what's happening in between is I have to touch every single possible value of my y's. As usual, if you have questions, please let me know. I'm happy to help. Good luck on this assignment, and I hope that you enjoy these problems.